Okay, in this section here we're going to be talking about particular solutions to, I hate to have to say this, but differential equations. I shouldn't be mentioning that. Alright, so it looks like we've got some function, and that same function is being shifted, let's say, I don't know, up or down. We've got some little line segments here on our graph. Wonder what that's all about. Okay, well, we've got a function here, f prime of x, and we've got we've got an equation over here. It looks like dy over dx is equal to 3x squared plus 4x. Wait a minute, that looks like this over here. Well, it actually is, except this is some different notation. This dy over dx, then it's the same thing as saying f prime of x. But depending on what we're doing, we like to change up our notation, and I'm changing it to instead of f prime of x, dy over dx here. All right. Well, let's take a look at this this equation over here, also known as our derivative. If I plugged a 0 into the derivative, we'd get 0 out. Now here on the x-axis is where 0 lives, and plugging 0 in, I get this line segment right here has a slope of 0. And look at this point on the curve here, it also has a slope of 0, and well, that has a slope of 0 also. What if, let's see, 2, 4, I don't know what this is. Man, I could have made this a little bit easier. If I took this point here on the x-axis and plugged it in, the x value into this, it turns out that that's what the slope of this little line segment would be. Now, this is kind of like the slope of the tangent line at this point right here, and if I kept the same x and plugged it in and went up to this one, and well, we get the same thing. And of course, same thing's going on over here. Take some negative x value, plug it in. I don't know, it looks like it's somewhere right in here. Plug it in, and this is what the slope of the tangent line would be at this curve and at this curve here. You're probably going, what? Well, let's say that we want to find the antiderivative. So this is the derivative, and we want to find the antiderivative. So we want to take the integral of this function, and we end up getting, well, this is what we end up getting. And hopefully at this point you know how to take the integral of this simple polynomial, right? Add 1 to the exponent, put the exponent down below. Okay, do the same thing here. Add 1 to the exponent, put the exponent down below. Simplify this thing down. And this is what we get. So this is our antiderivative, capital F I'm calling it, of x is equal to x cubed plus 2x squared plus c. Plus c. And that's what those graphs were that I had, where c was just a different number. Now let's go back to the graph. So this graph, right, is the x cubed plus 2x squared plus c. Now in this particular case, c happens to be 0. It's crossing right here where x is 0 and y is 0. And then if we were to shift the graph up 1 unit, right, we would tack that c would be a 1. So we'd have x cubed plus 2x squared plus 1. And so, right, and that's what we'd get here with this green curve. And then I do have some other curves up here. Okay. So we tack 2 on to the end of our antiderivative. We replace that c with a 2, and so now our curve has been shifted upward, and so forth. However, we want to find the curve that passes through the point 0, 1. And so we're going to let our capital F here, the antiderivative, f of 0 equal 1, and then we need to solve for c. Well, right, it turns out that c is just 1. And so this is the curve that we're interested in now. And that happens to be this green curve here. So these are called directed line segments, also known as if you filled up this entire plane here or whatever, we'd have a directed field. in